most important thing to bring with you from general chemistry is proficiency with drawing Lewis structures, and now being able to convert those to condensed formulas and bond line formulas. The second most important thing to bring with you from general chemistry, which will be absolutely crucial for the remainder of the course, is acid-base chemistry. And since it's likely that not all of you have brought everything from acid-base chemistry with you from general chemistry, I think it's important to do a little review of the definitions. There are 3 definitions that you should learn. And those are Arrhenius, you know how to define Arrhenius acids and bases, Bronsted-Lowry, define Bronsted-Lowry acids and bases, and Lewis. We should be able to define Lewis acids and bases. And in fact, Lewis acid-base chemistry is so important in organic chemistry that we will actually have new names for Lewis acids and Lewis bases so that we can distinguish whether we're talking about Bronsted-Lowry or Lewis acids and bases without having to specify which definition. The Arrhenius acid-base theory is probably one that we're not going to need very much, because the Arrhenius acid-base theory is based in aqueous solution, and in organic chemistry we're seldom working in aqueous solution. So an Arrhenius acid is something that increases the concentration of hydrogen ion in aqueous solution. And an Arrhenius base is something that increases concentration of hydroxide ion, again, in aqueous solution. It can increase the hydrogen ion concentration directly by donating a hydrogen. So hydrogen chloride, for example, when dissolved in water, completely dissociates to hydrogen ion and chloride ion. And lithium hydroxide solid, when dissolved in water, dissociates completely into lithium ion and hydroxide ion. But an Arrhenius base can also be something that reacts with water to form hydroxide ion, like ammonia, for example. So NH3 gas reacts with water, liquid, to form the ammonium ion, NH4+, and in the process creates hydroxide ion. And that's an equilibrium reaction. The hydroxide ion concentration is lower for the same concentration of ammonia as it would be for lithium hydroxide. Both of those are Arrhenius bases, though, lithium hydroxide and ammonia, because they both increase the hydroxide ion concentration in aqueous solution. Bronsted-Lowry acids and bases are not limited to aqueous solution, because the acid is defined as a proton donor. The Arrhenius acids and bases above are, in fact, also Bronsted-Lowry bases, right? The ammonia is accepting a proton to become the ammonium ion, so it's a proton acceptor. So it's an Arrhenius base and it's a Bronsted-Lowry base. The hydrogen chloride here is donating a hydrogen to water, and it would be more correct to write this as HCl liquid. Water acts as a base in this case to form H3O+. We know that H plus aqueous actually means hydronium ion. So in this case, it's a Bronsted-Lowry acid-base reaction where hydrogen chloride gas acts as the proton donor and water acts as the proton acceptor. In Bronsted-Lowry acid-base theory, though, we can have acid-base reactions and we don't have to have them in water. In fact, hydrogen chloride gas can react directly with ammonia gas to form solid ammonium chloride. HCl is the Bronsted-Lowry acid, the proton donor, and NH3 is the Bronsted-Lowry base, the proton acceptor. Lewis acids are electron pair acceptors, and Lewis bases are electron pair donors. This expands the definition of acid. There are compounds that can act as electron pair acceptors, but accept something, right, that do not donate a proton, that don't have any protons. BF3 is an example of boron trifluoride, which we saw earlier in the course as a Lewis structure that is electron deficient at boron. Boron atom can thus act to accept a pair of electrons from some other material, ammonia, for example. If its lone pair could donate its pair of electrons to boron trifluoride, form a compound. So BF3 is not a Bronsted-Lowry acid, but it is accepting a pair of electrons. Ammonia is both a Bronsted-Lowry and a Lewis base. If it has a Lewis base, if it donates its pair of electrons to a hydrogen, as it did in this reaction, then it's acting as a Bronsted-Lowry base. So there is a class of molecules that are Lewis acids that are not Bronsted-Lowry acids. There is no class of molecules that are Lewis bases that are not Bronsted-Lowry bases. It doesn't expand the number of things that can be bases. It only expands the number of things that can be acids. Because Lewis acids and Lewis bases are so important in organic chemistry, and we want to be able to distinguish between a compound which we're talking about acting as a Lewis acid and a compound where we're talking about Bronsted-Lowry acid, we will use the term acid and base to specifically refer to Bronsted-Lowry acid basicity, and we will use for a Lewis acid the term electrophile. Right? It's an electron lover that accepts the electrons, and for a Lewis base, we use the word nucleophile. It's a nucleus lover. It wants to accept a pair of electrons. So bases are nucleophiles. They want to donate their electrons to a nucleus which is positively charged. And acids are electrophiles. They want to accept a pair of electrons from something that has a pair to donate. So when we mean Lewis acid, we'll say electrophile. When we mean Bronsted-Lowry acid, we'll say acid. When we mean Lewis base, we'll say nucleophile. And when we mean Bronsted-Lowry base, we'll say base. And we really won't be working in aqueous solution, so the Arrhenius acid-base theory is not particularly relevant for the organic chemistry course, although it's one of the more important acid-base theories in analytical chemistry, where you're mainly dealing in aqueous solutions. So those are the three acid-base definitions. And what will be very important to us when talking about acids and bases, the Bronsted-Lowry acids and bases, is recognizing what the best acid is among a group, or recognizing which proton is the most acidic proton, and therefore the one that's going to be donated in a molecule that has a number of different hydrogens that could potentially be donated. And we will refer to the relative acidity of the various classes of acids that we're working with by using their pKa values. Recall that the p function means the negative log, so pKa is the negative log of Ka, and Ka is the acid dissociation constant. For an acid like acetic acid, which you now know is also called ethanoic acid, reactant its proton to form acetate ion. Now the conjugate base. And the chromium ion is now the conjugate acid. So we have our acid and our base. Reacting with each other. Bronsted-Lowry acid donating a proton to the Bronsted-Lowry base. The oxygen of the water acting as an electron pair donor, so it's also a Lewis acid-base reaction. The equilibrium constant for this reaction, which we write as Ka, and that's an acid dissociation. The acid donating its proton is equal to 1.8 times 10 to the minus 5. And that means that the pKa is equal to negative log 1.8 times 10 to the minus 5 is close to 5. It's about 4.76. But we're going to round to 5 and just say that carboxylic acids in general have pKa's of roughly 5. That's a weak acid. It's not fully dissociated, so most of the acetic acid in solution is still as undissociated acetic acid. But from the point of view of organic molecules, it's a relatively strong acid compared to other organic functional groups. Most organic functional groups are not particularly acidic on the overall scale of things, so it gets a lot weaker. So we'll refer to weak acids, and then we'll refer to very weak acids, and then we'll refer to extremely weak acids. So it's important to understand that Ka, the acid dissociation constant, is for this reaction, often shorthanded. So we will often actually not show the water, we'll just show it as H plus, aqueous plus. And an abbreviation for acetate is AC, so OAC, aqueous. The AC is understood to be this part, which is C2H3O. So AC represents CH3, C double bond O, and then this oxygen here. So sometimes the C, and that dissociates into H plus OAC minus. Right? So we need to know that the larger number, right, the closer this gets to 1, or even greater than 1, the stronger the acid. And thus the lower value for the pKa is the stronger acid. Because there's a negative log. The larger value for Ka is the stronger acid. But we will almost always, in organic chemistry, classify our acids as stronger or weaker than one another by giving the pKa value, not the Ka value. If we'd like to be able to figure out whether an acid-base reaction, a potential acid-base reaction, is very favorable, very unfavorable, or somewhere in between. And to do that, we'll actually have to know the pKa values for a reasonable number of compounds. There is a table of pKa values in your textbook. That's in chapter 2 on page 60. But there's also a table of the ones I would like you to know available on Blackboard that you can learn. And in some cases, I've rounded them. So my numbers are going to be a little bit different from the numbers that you'll see on page 60 in chapter 2. So we need to know, for example, that alkanes have really small Ka values, thus really large pKa values. pKa is about 50. Which means the Ka is about 1 times 10 to the minus 50. You can't actually even measure that in aqueous solution. It's effectively not dissociating at all. It's the weakest acid you can get. The pKa of a hydrogen attached to an alkene is about 6 orders of magnitude greater. So that pKa is around 44, or Ka of 1 times 10 to the minus 44. And a hydrogen attached to an alkyne has a Ka of around 1 times 10 to the minus 25, or a pKa of approximately 25. That varies a little depending on what else is attached to the alkane, the alkene, or the alkyne, but we can use 25 for an alkyne, and 44 for an alkene, and 50 for an alkane as pretty good approximations. Ammonia, NH3, is a very weak acid, has a pKa of about 35. Hydrogen, H2, has a pKa of about 38. And so again, these are very weak acids. Those are both weaker acids than this alkyne. And then we get into some things that are a little bit better. Those pKa values are in the range from 20 to 22, depending on whether it's an aldehyde or a ketone or what else is attached to it. So significantly stronger than the alkenes and alkynes, but still not particularly strong. Alcohols, ROH, tend to have pKa's somewhere on the order of 15, although that also depends on what's attached to the R group. If it's a trifluoro group, it's significantly lower than 15. And if it's a, what we refer to as tertiary butyl group, that pKa is about 3 orders of magnitude larger, and pKa is approximately equal to 18. Which means that T-butanol, or 2-methyl-2-propanol, methyl-2-propanol, also known as tertiary butanol, because the OH is attached to a carbon that has 3 carbons attached to it and no hydrogens. That's a significantly weaker acid, 1.0 times 10 to the minus 18 for its Ka, than methanol or ethanol. Stability of the oxygen anion in T-butoxide, because you have a large hydrophobic alkyl group attached, you can really only solvate that from one side, whereas for the small additions to solvating it on the right-hand side, on the left-hand side as well, less effectively solvated anion renders this less stable in solution, which makes it a stronger base, which gives it a weaker acid. But for the most part, we'll use 15 for alcohols. Those are kind of in the middle of the acidity scale in terms of the things we work with in organic chemistry. So we've got hydrocarbons that are very weak, although the alkyne is significantly stronger than the alkene, and the alkene is somewhat stronger than the alkane. Our amine and hydrogen, somewhere in the middle, attached next to a carbonyl group increases your acidity. And in fact, being next to a double bond, a regular double bond, increases your acidity as well. This is referred to as an allylate position. And the pKa of an allylate position is approximately 40, rather than the 50 that it would be if this double bond were not present. So being adjacent to a double bond increases your acidity. Carbon-carbon double bond, drops your pKa to about 40. Carbon-oxygen double bond drops. But these are all very weak acids, right? 1 times 10 to the minus 15 is still a small equilibrium constant. Other acids that it will be important to know are thiols. The SH group has a pKa around 10 to 12. We use 12 as just a round number. An OH group that's attached to a benzene ring is more acidic than an OH group that's not attached to a benzene ring. It has a pKa around 10, which is about the same as the pKa of hydrogen cyanide. HN3, hydrozoic acid. Has a pKa on the order of 5, which is about the same as your carboxylic acid group. Also has a pKa of around 5. In between these two, ammonium ion has a pKa of around 9. Says, find it. Now your textbook actually says this has a pKa of about 9 as well, so somewhere in that 9 to 10 range for hydrozoic acid and ammonia. Phenols at around 10. Hydrozoic acid and carboxylic acids around 5. And then on the far other end of things, the very strong acids, HCl, HBr, and HI, those have pKa's of 8, -8, -9, -10, respectively, which means they have Ka values that are much greater than 1. 1 times 10 to the 8th. 1 times 10 to the 9th. 1 times 10 to the 10th. A negative pKa value is associated with a strong acid that is completely dissociated. Only one part in 10 to the 10th is still hydrogen iodide gas. The rest of it is dissociated into hydronium ion and iodide ion. So these are the strong acids. Hydronium ion itself, which is the strongest acid that can actually exist in aqueous solution, has a pKa of -1.75. So anything that has a pKa smaller than that, -8, -9, -10, right? All of those are going to be completely dissociated. So you'll see things like nitric acid. Nitric acid has a pKa on the same order as hydronium ion of about -2, -3. Sulfuric acid's pKa is down there in that range as well, the other strong acids. So strong acids that you learned in general chemistry have negative pKa values. The weak acids that you learned in general chemistry have these pKa values, and it's on the order of 5 to 10 for the most part. And then the organic functional groups that we've talked about, the amines, the alkenes, the alkanes, the carbonyl groups, the allylic positions, those are very weak acids that have pKa's usually 20 and larger, 25, 30, 35, 40. So you'll want to learn those pKa values so that you know how much more acidic one functional group is than another. And what we'll also want to do is we'll want to understand why some things have such a low pKa relative to others, which